Hey everybody, today we are going to be looking at tables of equivalent ratios, which is lesson 1-2. So let's get right into it, find where we're going to start it. So we talked about exploring ratios yesterday and equivalent ratios, and just kind of getting an understanding of what a ratio is. It's a comparison of two things, okay? So you can compare it either part to part or part to whole. So we're going to continue on with that today and showing it through tables and other graphical displays. So when we're exploring ratios, here we have how we're going to use a model to find equivalent ratios. So Eliza is making pizzas for a party. Each pizza uses 2 cups of Greek yogurt and 3 cups of self-rising flour for the dough. We're going to model the number of cups of each ingredient Eliza will need to make 1, 2, and 3 pizzas. So our ratio, remember, is 2 to 3. So we're using 2 cups of Greek yogurt and 3 cups of flour. And that's what we would use as our graphical display. Okay. So this is what it would look like. Now we can also make this with more, right? So say we wanted to double the recipe. If we doubled the recipe, we would double the cups of Greek yogurt to have 4, and we would double the cups of flour to have 6. And that would be correct, right? That's an equivalent ratio. We're doing the same thing to each side of the ratio. So like I said, we could double it to make 2 pizzas. We could triple it, right, to make 3. We're multiplying 2 by 3 to get 6. 3 times 3, which is 9. And those would all be equivalent ratios. So what if we wanted to make 8 pizzas? Well, we simply would take 2 times 8, right, because this is for 1, 2 times 8, which would be 16, and 3 times 8, which would be 24. So our equivalent ratio would be 16 to 24. So as long as we're doing the same to both sides of the ratio, both parts, then we would have an equivalent ratio. Now, so once again, here's a demonstration of 1 pizza. Here's 2 pizzas and 3 pizzas. So we're using the same ratio, but then doubling and tripling it to show for more pizzas. So this is called a ratio table. You can see that it goes up by the same amount each time in the row, and whatever we're doing to one row, we're also doing to the next row. If we were adding, we would be adding to, or we can multiply, right? We're always going back to the beginning. I like to think about these more as the multiplicative because it keeps it organized in my mind, and I'm immediately thinking, okay, this first column here, 2 of 3, that's 1. This is 2. This is 3. Okay, so if we're multiplying by the number of pizzas, then that would give us the new ratio, and we're doing it to both sides. Okay, so we could continue this pattern further and further on. And what this is called is scaling. Okay, so we are using the same process or operation on both sides of the equation, or I'm sorry, the ratio, to then find the new ratio. Like I said, that's called scaling. Here's the word scaling right here, scaling. Okay, it's a very important word. Okay, we're going to talk a lot about it because sometimes you might not be able to find an equivalent ratio right off the bat, and you're going to have to do some playing around to find other equivalent ratios to then get what you need to get. So like I said, we'll talk a lot more about scaling in the future, but we're also going to do it now. So here we have making yellow icing. So we need 6 drops of yellow and food coloring with 2 cups of white. So we have the ratio of 6 to 2. Now, our question is, should Amida add less than, more than, or the same number of drops, 6, of yellow food coloring to mix with 8 cups of icing? Well, if we're going from this 2 cups to 8 cups, we're obviously going to need to increase the amount of yellow as well. 2 times 4 is 8. So we would need to do the same thing with the 6. We would multiply the 6 times 4. We would then get 24. Now, a really easy way to do this is to create a table. So our original ratio is 6 to 2. Now, if we needed to go to 8, we would enter it there, right? So let's check. Yep, that's what we needed to do. Okay, so we put in, like I said, the original problem, the 6 to 2 ratio, and then we put in the 8 in the box that we know. Now, obviously, we need to figure out the number of drops of yellow because 2 times 4 equals 8. We multiply 6 by 4, once again, to then obtain 24. Let's check our answer. Yep, we're good. So the ratios 6 to 2 and 24 to 8 are then equivalent. So Amita should mix 24 drops of yellow food coloring to get the same shade of yellow. So when we're using ratio tables, it's a really nice way to lay everything out for us and make sure that we can see all the equivalent ratios right there. I like to even use the sides to tell what I'm multiplying by to make sure that I am doing the correct thing. All right, so we're going to skip this one here. Now we can also work backwards. So if we have a larger ratio, we can then work backwards to find other equivalent ratios. Or if we know the parts, then we can figure out the rest. So Aquino mixes 3 sample containers of yellow paint with 4 samples of red, okay, to create his favorite shade of orange. His little sister wants to create the same shade, but she only has 2 sample containers of red paint. So we only have 2 here, okay? So we're going to need to figure out how much yellow to use. Now, we know that we cannot scale forward here because we actually have less than the original amount of red. So whatever we do, our answer needs to be smaller than the 3 here, okay, for the yellow. So once again, we can create a table and put in what we know. For every 3 containers of yellow paint, there are 4 containers of red paint. We know that we have 2 containers of red, okay? So now we have this table filled in, and now we just need to find this one last missing answer. So what did we do to 4 to get to 2? Well, we divided by 2. So we take 3 and we would also divide by 2 to get 1.5, right? 1/2. 1.5, sorry, 1.5. So the ratios of 1.5 to 2 and 3 to 4 are equivalent. So we know that she needs to mix 1.5 containers of yellow paint with 2 containers of red paint to create that same shade. All right, we're going to move on. Now we can also scale in 2 directions. Okay, so if we're missing a lot more information and we needed to find more ratios, we can then scale in both directions. So Natasha made raspberry punch for a party by mixing 9 ounces of fruit punch, 3 liters of soda, and 6 scoops of raspberry ice cream. Halfway through the party, the punch bowl was empty. Now, Natasha used some of her ingredients, so she only has 6 ounces of fruit punch left. We need to figure out how much ice cream she would need to make another batch. So once again, we are going to create a table. We know that the original ratio is 9 ounces of fruit punch and 6 scoops of raspberry ice cream, but we know that we only have 6 ounces left, okay? So that would be what we know, okay? Now, like I said previously, it's not easy to just go directly from 9 to 6, right? There's no whole number that you can multiply or divide by to immediately get to 6. So we need to think, what can I do, or what factors can I use that would allow me to get from 9 to 6? So what we do is we actually scale further past that 6 to get down to 3, right? 6 and 9 both have the factor of 3. That's their greatest common factor. That would then be the number that we would use. Well, what did I do to get from 9 to 3? Well, I divide by 3. So I also need to take 6 and divide by 3, which is 2. So now we get a ratio of 3 to 2. 3 to 2 is equal to 9 to 6 in terms of ratios. So now we can go from 3 to 6. Well, we're simply multiplying by 2, which means I'm going to do 2 times 3, 2 times 2, which is then 4. Once again, the ratio 6 to 4 is equivalent to 9 to 6 and 3 to 2. All three of these ratios are equivalent, and we were able to find our answer that she would need 4 scoops of raspberry ice cream. So because we were not able to immediately get from 9 to 6, we had to find another factor, which was 3, and we were then able to find our answer fairly quickly. So let's take a look at this one. A pack of trading cards are on sale, 10 packs for $4. So we're going to start by writing our ratio. Okay. I'm going to write my ratio, and we can make it in a table. So we have number of packs, and we have the cost. Okay, so our original ratio here is 10 to 4, and I need to get to 35. Now, obviously, and this is then the question that we need to answer here is, what would we put in this spot here? I can't go from 10 to 35, so we need to pick another factor. So the greatest common factor of 10 and 35 is actually 5, right? So I'm going to put a 5 here. Now, if I'm going from 10 to 5, I am dividing by 2. Well, I would do the same thing here, divide by 2. 4 divided by 2 is 2. Now, I can go from 5 to 35 by multiplying by 7. Well, if I do that to the top, I also have to do that to the bottom, times 7. So my answer here would then be $14. Well, let's check our answer. Based on our table, that's what we came up with, and we are good to go. That is the correct answer. So like I said, that is an example of scaling. We're going and finding another factor that would then lead us to the answer that we actually need. Now, another way we can do this is to actually use a double number line. Double number lines are just what they sound like. A number line and another number line stacked on top of each other. These number lines let us line up our answers, our equivalent ratios on top of each other, and then we're able to move quickly and find all the answers. Now, is it always the best strategy to use? No. Number lines are time consuming to make, but they lay out all your answers immediately. Okay, so you wouldn't have to do as much scaling. So what we would do, let's go back to the situation. We're making biscuits, right? So to make 24 biscuits, we use these ingredients. Now we only need to make 18. So how many cups of flour does she need? Okay. So we're going to use a double number line to solve this problem. So this, like I said, is a double number line. It's just 2 number lines, and we put the ratios on them. Okay, so this would be your one part, this would be to your total. Okay. Now, what we can do here is find equivalent ratios. So if this is 4, I can then add in 4 lines, 1, 2, 3, 4, right? So that we can then figure out how much it would be for using only 1 cup of flour, 2 cups of flour, and 3 cups of flour. So When I go from 4 to 1, obviously we're dividing by 4, so 6 divided by 4. I'm sorry, 24 divided by 4 is 6. So our ratio would be 1 to 6. We are then able to find the other values that we would fill in there. So 2 to 12, 3 to 18. Those would all be equivalent ratios. Now, what we needed to do was to figure out 18 biscuits. Now we can easily see it in our double number line that she would need 3 cups of flour. We're good. Moving on. Okay. So when we're using ratio tables and double number lines, we're able to see all the ratios that would be equivalent fairly simply. Double number lines do take a little more time and space if you're drawing it out, but it's easy to see a lot of the ratios all laid out together. Whereas with a number line, or I'm sorry, a table, you can go immediately to your answer. All right, so at this point, that's all that I have for you guys today. Reminder to be checking Schoology to find your assignments, and let me know if you have any questions.